All right, welcome everybody to section 5.1. This is going to be our introduction to the quadratic functions. This chapter is going to be very important for us in the long run, and everything that we do kind of comes back to this. All of our polynomial functions, all of our rational functions are going to come back to a lot of the stuff that we learn here in the quadratic function chapter. So we're going to look at just identifying quadratic functions. We're going to be looking at their graph and a couple of things that we can look at from the graph itself. So the first thing that we have to do, though, is we have to look at what's called the FOIL method. You might recall this from previous math classes. The FOIL method is just a simple method to help you multiply things of a certain form. And the form is going to be when things look like, if I can get my pen here, look like this when they're in two parentheses, and it looks a little bit something like this: x plus 1 and x plus 7. And we need to know how to multiply this together. And this is just a simple method. Again, as I said, it's a FOIL method. FOIL actually is an acronym that stands for first, outer, inner, and last. And it's just a way to help you make sure you get all of the multiplication pieces that are necessary. And this is kind of what it's going to look like. It's going to look like this. So if I had the multiplication of x plus 7 times x plus 9, my first, the f part, is the first, the x times the x. The outer is the outer two pieces, so it's going to be the x times the 9. The inner are the inner two pieces, which is the 7 times the x. And the last would be the last two terms, so the 7 and the 9. And what this does is, again, it's just a simple way of remembering how to multiply two of these things, right? So here, if I was to do the FOIL method, if I was to look at first, I would have x times x, and x times x is going to be x squared. So this would be from my f. My outer is going to be x times 9, and that's going to be positive, right? Because it's positive 9 times positive x, so it's 9x. That's my outer. My inner is going to be 7 times x, and again, it's positive as well. And that's my inner. And my last is going to be 7 times 9, and my 7 times 9 is 63. And again, they're both positive, so my answer is positive, and that would be L. And then when we do this, we need to simplify in standard form. So we're going to say x squared. I have a 9x and a 7x, which makes a plus 16x, and then plus 63. Now, more often than not, this is going to be equal to y, and therefore this was equal to y. And so this is equal to y as well. So y is equal to x squared plus 16x plus 63. So let's take a look and try another example. Sorry about that. Not sure what just happened there. Let's look at another example. Let's say we have 2x plus 3 times 3x minus 7. If I was to do the FOIL method here, I would say my first is 2x times 3x. So it's f first times the first. So 2x times 3x is going to be 6x squared, because 2 times 3 is 6, and x times x is x squared. Then I'm going to go outer, which is a minus 7 times a plus 2x, which makes a minus 14x. Then I have my inner, which is a positive 3 times a positive 3x, which is going to be a plus 9x. And then my last is going to be plus 3 times minus 7, which is minus 21. And we always simplify our answer to standard form. We get 6x squared minus, we got minus 14 plus 9, which is minus 5, minus 21. And there we have our standard form of our quadratic equation or function. All right. Now, we are going to be using this idea in the very first thing when we look at quadratics. And what it is really just a classifying. We want to figure out if the statement that's been shown is a quadratic or a linear type function. So in order to do this, we need to simplify the expression to standard form. So just like we just did with that FOIL method. And we need to determine, this would be the question, determine if the function is linear or quadratic, identify the quadratic, linear, and constant terms. So here are my two examples. And on the first example, we have a product of two, what we call binomials, because there's two objects. 2x and 3 is binomial, right? So we have a product of two binomials. So we need to determine by foiling this if it is a quadratic equation or if it is a quadratic function or a linear function. So here we get 2x times x, which is 2x squared. Okay, so that was first. I'll make sure I do my arrows here. My outer is minus 4 times 2, so I get minus 8x. My inner is 3 and x, which makes it 3x. And my last is 3 times a minus 4, which is minus 12. Simplified down to standard form, we get 2x squared. Minus 8 plus 3 is a minus 5x. Minus the 12. So this is a quadratic, so it is quadratic. And if I wanted to determine the quadratic, linear, and constant terms, I just look at this and say, okay, the quadratic term is 2x squared. That is my quadratic term. The linear term is the one with x to the first power, so that is a minus 5x. That's my linear term. And my constant is the one without the x, so that's a minus 12 or negative 12. And that's my constant term. Right? Quadratic because it has x squared, linear because it has x to the first, and constant because there's no x. All right, let's think about this one here, the second one up here. Okay, so if I wanted to do this, there's no foiling involved, but there is a distributive property. I have to distribute the 3 on top of both of these, so this becomes 3 times x squared minus 2x times 3, which is a minus 6x. I have to also distribute this. I want to make sure you understand that we are distributing a minus 3 onto both of them, so we get a minus 3x squared. Then we get minus 3 times minus 2, which is a plus 6. Simplified to standard form, I get 3x squared minus 3x squared, which is 0. And then I'm left with minus 6x plus 6. So we notice that there is no quadratic term, and therefore, and because it's just negative 6x plus 6, this is linear. So if I was to look for the quadratic term, we could say 0, but we could also say there is none. The linear term is going to be the piece with just the x, so it's a minus 6x. And the constant term is a positive 6. So that's how we classify our functions. Right now, I don't think we'll have anything bigger than linear or quadratic. We shouldn't because we haven't learned them yet. So let's go ahead and move on to the next piece of information, which is going to be the parabola. So what we have to understand is the parabola is what we call the shape of the curve for the graph of a quadratic function. And it does kind of look like a smiley face, or we could have the sad face going in the downward direction. And the parabola is a very interesting thing because it is symmetric about its vertex. Which means the things on the right-hand side are exactly the same as the things on the left side of the vertex. Now, we actually have this axis of symmetry, which is that whole idea that something is the same on either side. So, what can we do? Things we can see on this parabola. So, one of the things that we can do is we can describe the vertex, or we can name the vertex. The vertex in this parabola is the lowest most point on this particular parabola, and it lies right there at the point 1, negative 1, because to get to the vertex, I have to go right 1, down 1 from the origin. Then, if I wanted to think about the point Q, the point Q is the point 2, 0. Notice that to go from 0 or 1, negative 1, to go from the vertex to Q, I went 1 to the right. The axis of symmetry tells me that if I have a coordinate that is 1 unit to the right of the vertex, it has a mirror image 1 unit to the left of the vertex. And since 1 unit to the right is 2, 1 unit to the left is going to be 0, so from the negative 1. And that means the y values are going to be exactly the same in order for it to have symmetry. So showing that we have the point 2, 0, or the vertex of 1, negative 1, it shows that we have a coordinate also at 0, 0. And yes, we can see that by looking at the graph, but if we did not have the graph in front of us, we could do this. We could say, okay, I have a vertex at 1, negative 1, and if I went right 1, up 1, I could also go left 1, up 1 to find 2 more points. We can do the same thing for the value of p. P in this case is negative 1, 3. Negative 1 is 2 units to the left, which means I can go 2 units to the right and get the same y value. 2 units to the right of 1 is 3, and I'd have the same y value. And again, you would notice that 3, 3. But again, if we did not have that on we did not have a graph, we could say, okay, if we had negative 1, 3, I would know, since this goes 2 units to the left, I can go 2 units to the right and find the same y value, and then I can connect the dots of my parabola. Please note that the parabola is not a V-shaped graph. It is not the same as the absolute value. So you do not get to use a straight edge on this graph when we start graphing parabolas. All right, you'll notice that that axis of symmetry here on this particular graph goes down at negative or at positive 1 on the x. And we use that symmetry to show, okay, well, there's plus 2 units this way and minus 2 units this way. In the textbook, because this is called Q, we will often call this Q prime, or Q with a little dash above it. And the same thing goes for P and P prime. We actually, in geometry, we called those prime because that was the image of Q. It was like the reflection. Q and Q prime were images of each other. All right, so those are the things that we can see on a parabola. What do we have left, if anything? Oh, looky there, we have an assignment. If you already received the assignment sheet, we're going to change that assignment, and we're going to put this on there for 5.1. And if you have not received the assignment, this is the assignment for chapter 5.1. and I will get you a new assignment sheet tomorrow. I will see you guys in class. I hope you learned a few things, and happy studying.